All right, let's dive right into a concept that is, no exaggeration, at the absolute heart of how your computer, your phone, pretty much everything with a chip in it gets its incredible speed. We are talking about pipelining, a truly genius idea in computer architecture. If you've ever wondered how processors got so mind-bogglingly fast over the years, the journey to that answer really begins right here. So let's unpack how this one idea completely changed the game for CPU performance. But, to really understand the solution, we first have to understand the problem. And to understand the problem, we need to know the rules. There's a fundamental principle that governs processor speed, and it's not just about shrinking things down. And here it is. This is the iron law of processor performance. It basically says that the time it takes a CPU to run a program boils down to three key things: how many instructions there are, the average number of clock cycles each instruction takes, we call that CPI, and of course, how long each of those clock cycles is. If you want to make a CPU faster, you have to shrink one of these. These are the three main levers that architects get to pull. Okay, so with the iron law as our guide, let's take a look at the first attempts to build a faster processor. Think of these as the early chapters in the story, and each one teaches us a really important lesson about what not to do. So, the first two big ideas on the table were single-cycle and multi-cycle designs. One was super simple but, well, painfully slow. The other was a bit more clever, but it came with a whole new set of headaches. The single-cycle processor is pretty much what it sounds like. It does one whole instruction in one single clock tick. That gives it a perfect CPI of 1, which sounds great, right? But here's the fatal flaw. The length of that clock cycle has to be long enough for the slowest possible instruction to finish. It's like a convoy that can only go as fast as its slowest truck. So even super fast instructions are just stuck waiting, which makes that clock cycle time massive, and the whole system just crawls. So the next idea was the multi-cycle approach. Architects broke each instruction down into smaller steps, like fetch, decode, execute. This was smart because it let them use a much faster, shorter clock cycle. They basically fixed the clock cycle time problem. But in doing so, they created a new one. Now, each instruction took multiple cycles to finish, which completely wrecked their CPI. It was a classic performance trade-off. And here's the thing. Both of these designs had the same fundamental problem. No matter how you sliced it, huge parts of the processor, the math units, the memory, the registers, were just sitting around, idle, most of the time. It was a massive waste of potential. All that powerful hardware, just waiting for its turn. This problem of idle hardware is exactly what led to the pipelining breakthrough. It was this incredibly elegant solution that was actually inspired by something much more low-tech, the factory assembly line. This got designers thinking, asking a huge what-if question. Since each stage of an instruction, fetch, decode, execute, uses a different part of the CPU, what if we could overlap them? What if we could be fetching a new instruction at the exact same time we're decoding the last one and executing the one before that? And that is the absolute essence of pipelining. It turns the processor into an assembly line for instructions. Instead of waiting for one instruction to completely finish before starting the next one, a new instruction enters the line on every single clock cycle. This keeps every part of the processor busy, all the time, just cranking out work. Now, to really get why this assembly line idea is such a game changer, we need to get clear on two key performance words: latency and throughput. They might sound kind of similar, but the difference between them is everything when it comes to understanding pipelining. Okay, so latency is just the total time it takes for one single instruction to go all the way from start to finish. Pipelining doesn't actually make that any faster. In fact, it can sometimes add a tiny bit of overhead. But the real magic is in throughput. That's the rate of finished instructions over time. By completing an instruction on every clock cycle, our assembly line just sends the throughput into the stratosphere. So that's the theory, but let's look at the actual numbers. This is where the beauty of pipelining really hits home and we see the massive performance gains. Check this out. The single-cycle design, it has that great CPI of 1, but its clock period is a sluggish 900 nanoseconds. The multi-cycle design gets that clock way down to 205 nanoseconds, but look what happened. The CPI balloons up to 4. And then there's the pipeline processor. It gets the best of both worlds. It keeps that super fast 205 nanosecond clock cycle, and it gets back to that ideal CPI of 1. And when you chart it out, the results are just staggering. the time it takes for instruction plummets from 900 nanoseconds for single cycle and 820 for multi-cycle, all the way down to just 205 for the pipelined architecture. This isn't just a small step up, it is a revolutionary leap in performance. It's not even in the same league. So the huge takeaway here is that pipelining breaks that trade-off that held back all the early designs. It lets you have a fast clock and finish one instruction per cycle, ideally. This is the breakthrough that unlocks just massive throughput. Trying to process multiple instructions at the same time, it sounds like a recipe for total chaos, right? So how does the CPU actually manage all this complexity without instructions tripping over each other? Well, that's what we're going to get into in part 2 of our explainer. We'll trace an instruction through the 5 classic stages of the pipeline. See you then.